Dear students, welcome to the today's session, Distributed Operating Systems. You all know very well that the modern computing architecture uses this distributed operating system concept because the main attraction of distributed concept is sharing of resources by the processes. But when you share the resources by the processes, there will be some problems we may face. So how to handle these problems? We'll see in detail. The first one is mutual exclusion. What is mutual exclusion? A file, that is a resource, must not be simultaneously updated by multiple processes. That is, multiple processes can access the resources simultaneously, but they should not update the resource simultaneously. That is the problem. So the files or the resources must not be simultaneously updated or modified. This is called mutual exclusion. For example, we all know very well that a printer is always restricted to a single process at a time, wherever the environment is, whichever the environment is, because then only we'll get a proper output. In the same fashion, in the distributed environment also, all the resources must be given the permission for updation only one per process. So exclusive access to such a shared resource by a process must be ensured. This exclusiveness of access is called the mutual exclusion between the processes. How to implement this mutual exclusion? There are three approaches: centralized approach, distributed approach, and a token ring concept. The centralized approach is a conventional one. The distributed approach and the token ring concepts are most of the systems today follow. So first we'll see what is a centralized approach. Centralized approach, of course, the title itself will give you an idea. That is, there is one central process which controls the actions of other processes. For example, here the PC is the control process. So this process gets requests from P1, P2, P3 like other processes, and it consider those requests, and according to priority or some other concept, it either releases the resources or deny the resources permission. So according to that, it gives a proper reply to other processes. So the processes, when they make a request to the coordinate control process, they have to wait till they get the reply whether they have been allocated the resource or not. So the entire control is with the control process. The other process are simply make a request, get either resource or not, otherwise they have to wait. This is the centralized approach. The next one is the distributed approach. This is somewhat democratic approach. The distributed approach is a democratic one. So here all the process are given equal power or permission. That is, the decision making for mutual exclusion is distributed across the entire system. So all the process which they want to enter the critical section, they cooperate with each other. What is a critical section? The critical section is a section, that is the period in which a process requests for the shareable resource. Once it gets the permission, the resource is exclusively used by that process, and then after the use, it exits or release that process. So that entire time period where the resource was used by the process is called the critical section. So to use this resource exclusively or to enter into critical section, both are same. They should cooperate with other processes in the environment. So when a process wants to enter critical section, it sends a request message to all the other process to get their consent. Now this diagram will clearly explain the situation. See the first one, that is A. There are four processes P1, P2, P3 and P4. P4 is already in the critical section. That is, a resource has been allocated to this P4 and the same resources now needed by or required by P1, P2. P3 is not at all bothered. It is busy with some other activity. Now see the timestamps of P1 and P2. P2 has a timestamp of, that is TS, of 4 and P1 has a timestamp of 6. That is, P2 has sent the request little bit earlier than P1. Okay, it is 4 and after that only, that is at 6, P1 has issued the request. So now P1 has sent a request to P2, P3 and P4 according to the distributed approach. These three processes receive these requests. Now P3 is not at all bothered, so immediately it sends a OK. P4 will not respond because it is in the critical section. And how about P2? P2 has a timestamp little bit earlier than P1. So P2 will not send a reply to P1. So considering these, now P1 has to send a OK message to P2. That is in the figure B. And P3 has to send a OK message to both P1 and P2 because it not at all requires that resource. And there won't be any response from P4. Now, in the queue, you can see two processes, P1 and P2. And P2 is in the first position and P1 is kept after P2. Okay, which means when the P4 exits the critical section, permission will be given first to P2, then only to P1. Okay, see the message. See the next diagram C. Now, P4 exits the critical section and immediately it checks whether it has received any messages. Yes, it has received message from both P1 and P2 and it sends a OK message to both P1 and P2. Now, P2 has got a consent from P1, P3 and P4. So now P2 enters into the critical section. Once it completes, it exits the critical section and it should send a OK message to P1. Then now P1 has got consent from all the other three processes. So it enters into the critical section. Once it gets complete the process, then it will release the resource. This is the distributed approach of processes P1, P2, P3, that is more than one process in the environment. Hope you understood this. The next one is the token passing approach. The token passing approach is, by the name itself, you can understand, circulating a single token among the processes. So the mutual exclusion is achieved by circulating a token among the processes. Okay, fine. The processes are arranged in logical ring structure, that is round. It's a round structure, logical ring structure. Okay. What is a token? Token is a special type of message. So this message is circulated among the processes and that message entitles its holder to enter critical section. That is, whoever wants to enter into the critical section, they give a tag like its ID and then they circulate this token among all other processes, which mean I need that resource. I am going to enter into the critical section. Anybody wants to do the same. So if nobody wants, they will simply pass on the token. So if the token is passed among the processes and finally it reaches the same sender, sender assumes that the critical section is exclusively given for that process because nobody has obtained or locked the token. The token was circulated among the ring structure. So everybody has passed, just they passed the ring token. So finally the token reaches the sender, the same sender who issued that. Okay, so the sender found, he assumed or he is very sure that nobody needs that resource. So he enters into that particular process. enters into the critical section. So token can be moved either clockwise or anti-clockwise in any direction. Both the direction is permitted. When a process gets token, it can enters into the critical section, and after finishing the work, it exits from the critical section and it passes the token to the neighbor process, indicating that I have completed. If anybody else requires, you can simply pass the token. So in this way, the token passing, by means of the token passing approach, the mutual exclusion is achieved. See, you can see the diagram. See, there are so many systems and the token is indicated like a box. Actually, it is a message. It is circulated. You see, now it is in the anti-clockwise direction. Okay. So the mutual exclusion is one type of problem in the distributed approach. The other major one is the deadlock. So what is a deadlock? You can see the diagram. There are two processes, P1 and P2. And there are two resources, R1 and R2. Resource R1 is held by P1, which is used by P1. But the process P1, it expects or requires R2 also, it requires R2 also to finish the process. Similarly, P2 already it holds the resource R2, but to complete it, the process, entire process, it needs R1. It requires R1. So what is the situation now? R1 is held by P1, but P2 is waiting for R1 to complete the process. R2 is held by P2, but P1 is waiting for R2 to complete the process. Both the processes, P1 and P2, do not know that those R1 and R2 are held by each other. So this will, in this situation, will never complete. It indefinitely will go. Both the process will be in the waiting state because they won't get R1 and R2 because they are locked between each other. So this situation is called the deadlock. Now, suppose if you are having more than one units of same resource. See here, the R1, we are having two resources, two units of same resource, sorry, two units of the same resource. But both the units are allocated to the process. First unit is allocated to P1 and the second unit is allocated to P3. So there is no free unit. This is also a problem. Even if you have more than one units of the same resource, but no unit is free, then also we will face the deadlock. Next one. So what are the necessary and sufficient conditions for deadlock? Necessary condition is a cycle and the sufficient condition is a knot. What is a cycle? You can see the diagram. See from P1, P1 R2 to P2, P2 to R1, R1 to P1. This is a cycle. If there is a cycle, then there is a deadlock. Okay. Another cycle you can see R2, P2, R1, P3, R2. This is also a cycle. So again, if there is a cycle, there is a deadlock. Fine. This is a necessary condition for a deadlock. What is a sufficient condition? When there is a knot. Knot, you already know, there are two rings interlocked with each other, two cycles. Okay, so that is a knot. The cycle may be somewhat simpler to release, can be removed, but the knot is not that much easy to remove. So here you see R1, P1, R2, P2, R1. This is one cycle. And another cycle within the cycle. R2, P2, R1, P3, R2. So it is like a cycle within the cycle, which is a knot. It is, if there is a knot, this is a sufficient condition for deadlock. We can say that 100% sure there is a deadlock. The system should be, we should check the resource or allocate some resource or release some resource. Something has to be done. Okay. Next. See, whatever so far we have seen a graph that is called allocation graph. So in the allocation graph, the processes are indicated by circles and the resources are indicated by rectangles. So this is an allocation graph. Now, to simplify this, we'll move on to a wait for graph. In the wait for graph, the resources are removed. Then only the processes are shown. So you can see here P1, P2 and P3. So just by seeing this WFG itself, we can say that there is a deadlock. You see, P1 is connected to P2 and P1 is to P1, P2 to P1. So both are connected to each other. So obviously we can say there is a deadlock. So this WFG, wait for graph, is somewhat simpler compared to allocation graph. How to detect deadlock in a large environment? Because distributed means it is a spread way. Okay, there will be various sites, not only one. So here, for example, we have seen 4 sites: site S1, S2, S3, S4. There are 4 different sites in the distributed environment. So in the 4 sites, in each and every site, of course, they are independent of each other. But since it is sharing, distributed is sharing, so some of the process here may share the resource of another site. Okay. Similarly, some of the resources may be used by some of the process in another site. So sharing, it is a sharing. And now here what we are seeing is a hierarchical approach. A hierarchical approach is the base, starting from the base, will be reaching the top. This is a hierarchical approach. The simplification is done from the bottom to the top. That is from the root to the leaf. This is the hierarchical structure. So always in the base, you'll be more number of sites, and finally in the top, you'll be having only one site. Combination of all the sites. Now you see site S1 in site S2, there are processes and resources sharing each other. Resources are shared by the processes in both the sites. Combining these two, we have got a WFG, wait for graph, just by removing the resources. You can see there. So P1, P3, P2, there is a deadlock, but in the other diagram, there is no deadlock. Similarly, site S3 and S4 are combined to form a new WFG, and there also you have seen P5, P6, P7, but there is no deadlock as such. We have what we see. But if these two sites are combined, E and F, they are combined, we get at site G, and you see there is a deadlock. There is a deadlock, So P1, P2, P3, P4, P5, P6, P7. So just by seeing the base, we are not able to detect any deadlock. Okay, one more level. We are able to detect some deadlocks in the environment. But finally, everything is combined into a single site. We can see what is the actual situation. So the actual situation is, it is alarming situation. You see, there are 2 deadlocks. So immediately they should be detected and should be resolved. Okay. The next one is, okay, how to avoid these deadlocks? Because prevention is better than cure, isn't it? So how to avoid these deadlocks? Already I have told you, if the resource allocation is not done carefully, the system moves from a safe state to unsafe state. Because some of the resource allocation should not be done immediately. You have to forecast. So it may happen. This process may require this. Okay. So we are having algorithms for this. Based on those algorithms only, the resource allocation should be done efficiently. Then only the system will be somewhat in a safe state. Otherwise, often it will move from safe state to unsafe state. All the resources should not be allocated at a time, and a minimum number of resources must be kept in the free state to avoid deadlock. This is another solution. A minimum number of free resources must be kept to avoid the deadlock, because if there is a deadlock, then immediately the free resource can be allocated to that expected process, then the deadlock can be resolved. Deadlock, finally I can say, deadlock reduces the system performance, hence it should be totally avoided. Okay. Hope you understood the 2 problems we are facing in the distributed approach. The first one is mutual exclusion and the second one is deadlock. Okay, girls, okay, students, we'll meet in the next session. Thank you.